Inside a lab in Harbin, China, researchers dissolve raw bamboo fiber down to the molecular level in a beaker of non-toxic solvent, then coax those same molecules to reassemble themselves into a hard, glossy material that looks and behaves almost exactly like ordinary plastic. Except this version disappears back into the soil within 50 days. That is real. It exists, it's been published in a peer-reviewed journal, and it directly solves a problem that had quietly defeated nearly every biodegradable plastic alternative attempted before it. Every figure in this video comes directly from the published research and independent science reporting that verified the study's own data, because a claim this significant deserves genuine scrutiny rather than just a viral headline. By the end of this video, you'll understand exactly why this specific material succeeded where so many earlier attempts failed, and just as importantly, what still stands between this lab result and your kitchen cupboard. Here's where this story actually has to start, because you can't understand why this specific breakthrough matters without first understanding the exact trade-off that had trapped biodegradable plastics for decades. Conventional plastic, derived from crude oil, earned its place at the center of modern manufacturing, specifically because it's remarkably strong, cheap, water-resistant, and durable. But that same durability is precisely what makes it an environmental catastrophe once it's thrown away, with ordinary disposable polystyrene products taking centuries to break down in a landfill. Here's the problem that had limited every previous attempt at a genuine fix. Biodegradable plastics, including common alternatives like polylactic acid and polybutylene succinate, do break down naturally in soil, avoiding that centuries-long landfill problem entirely. But they've consistently suffered from a persistent, well-documented weakness: poor mechanical strength compared to conventional plastic, meaning they simply couldn't hold up to the same real-world demands as the material they were supposed to replace. Think about what that trade-off actually meant for the entire biodegradable materials industry for years. Engineers kept being forced to choose between a plastic that was strong enough to actually use and a plastic that was environmentally responsible enough to actually matter, with no material managing to genuinely deliver both properties at once at real industrial scale. Here's the team that finally found a way through that exact trade-off. Researchers at Northeast Forestry University in Harbin, working alongside a collaborator from Shenyang University of Chemical Technology, led by scientists Haiping Yu and Dawei Zhao, published their findings in the peer-reviewed journal Nature Communications on October 7th of last year. Here's the core idea behind their approach, and it's a genuinely different strategy than simply tweaking an existing biodegradable plastic recipe. Rather than starting from petroleum or blending together various plant-derived polymers, the team built their entire material around bamboo cellulose, the structural fiber that gives bamboo its famous natural strength, engineering an entirely new molecular reconstruction process specifically designed to preserve that natural strength inside a genuinely biodegradable finished product. Here's the mechanism behind how they actually pulled that off, and this is where the real innovation lives. The team used a non-toxic, alcohol-based deep eutectic solvent specifically formulated to dissolve bamboo cellulose all the way down to the molecular level, breaking apart the natural hydrogen bond network that normally holds bamboo's fibers together in their raw form. Think about what breaking that natural structure down to the molecular level actually accomplishes. Rather than simply grinding up bamboo fiber and pressing it into a new shape, the way many earlier plant-based materials had worked, this process genuinely takes the material apart at its most fundamental molecular level first. Creating a blank canvas, the researchers could then deliberately rebuild into a stronger, more purpose-built structure. Here's the second half of that mechanism, and it's just as important as the initial dissolving process. After breaking bamboo cellulose down to individual molecules, the team used what they call ethanol-mediated molecular stimulation to guide those same molecules into reassembling themselves, reconstructing a new, deliberately denser network of hydrogen bond interactions than the one that existed in the bamboo's original natural form. Here's why rebuilding that molecular structure denser than nature's own original version actually matters so directly to solving the strength versus biodegradability trade-off. Hydrogen bonds are exactly the microscopic connections responsible for holding any cellulose-based material together, and by deliberately engineering a denser, more optimized bonding network during the reconstruction phase, rather than simply accepting whatever structure raw bamboo happened to grow in naturally, the researchers could specifically target mechanical properties competitive with conventional plastic, while keeping the same fundamentally biodegradable cellulose chemistry underneath the whole structure. Think about what that two-step process, dissolve completely and then deliberately rebuild stronger, actually represents as an engineering strategy. It's the molecular equivalent of melting down an existing metal alloy and recasting it with a more optimized internal crystal structure. rather than simply reshaping the original metal while leaving its underlying atomic arrangement untouched. Here's the number that shows exactly how successful that reconstruction process actually was. The resulting material, which the research team named bioplastic, short for bamboo molecular plastic, achieved a maximum tensile strength of 110 megapascals in testing, a figure the researchers specifically confirmed. Outperformed several widely used conventional and biodegradable plastics, including polylactic acid and ABS, on a range of mechanical properties. Here's what a tensile strength that high actually means in practical terms. Tensile strength measures how much stretching or pulling force a material can withstand before it physically fails. And bioplastic's rating in this specific test genuinely rivals or exceeds materials already used in real consumer products and packaging today, rather than sitting in the noticeably weaker performance category biodegradable plastics have traditionally occupied. Here's the second key number from the same published study. The material also achieved a flexural modulus, a measurement of how well a material resists bending and deforming under load, of approximately 6.41 gigapascals, alongside thermomechanical stability above 180 degrees Celsius, meaning this material doesn't just resist tearing, it also holds its shape reliably under real mechanical stress, and stays structurally stable even when exposed to genuinely significant heat, a combination that opens the door to a far wider range of practical applications than a plastic that only performs well in one of those categories alone. Here's the number that gives this entire video its title, and it's the detail that actually solves the trade-off covered at the start of this story. Despite matching or beating conventional plastics on raw mechanical strength, bioplastic fully biodegrades in ordinary soil within approximately 50 days. Think about what achieving both of those properties simultaneously actually represents compared to every earlier attempt covered earlier in this video. This isn't a material that sacrifices strength for biodegradability or biodegradability for strength, the exact trade-off that had defined this entire research field for years. It's a single material genuinely delivering both properties at once in the same published study, verified through the same peer-reviewed testing process. Here's an additional property the research team specifically highlighted that goes beyond simply solving the original trade-off. bioplastic also demonstrated closed-loop recyclability, retaining 90% of its original mechanical strength even after being fully broken down and reprocessed, meaning the material isn't limited to a single use, single life cycle existence even before it eventually returns to the soil. It can genuinely be recycled and reused multiple times first, only fully biodegrading once its useful working life as a manufactured product has actually ended. Here's the final practical detail that matters enormously for whether this material could ever realistically replace plastic at scale. The researchers confirmed bioplastic can be processed using injection molding, traditional molding, and standard machining techniques, the exact same manufacturing infrastructure already used to produce conventional plastic products today, rather than requiring an entirely new, expensive manufacturing process built from scratch. Before going any further into where this specific breakthrough genuinely still has real questions ahead of it, it's worth pulling back and understanding that bioplastic isn't an isolated research project happening in a vacuum. It's one very visible piece of a much broader, deliberate national strategy already actively unfolding across China's bamboo industry. Here's the government policy context driving urgency around materials exactly like this one. China officially upgraded its national plastic restriction order in 2021, imposing stricter ongoing limits on the production, sale, and use of conventional plastic products, creating direct regulatory pressure, specifically motivating Chinese industry and research, institutions to find genuinely viable replacement materials rather than treating the search as a purely voluntary environmental initiative. Here's how far that broader bamboo substitution push has already reached beyond this single plastic breakthrough. Earlier this year, a bamboo-based tilt-rotor drone successfully completed its maiden flight in Tianjin with bamboo, composite materials making up more than 25% of the aircraft's entire fuselage, a level of bamboo integration the director of the International Center for Bamboo and Rattan specifically described as unprecedented anywhere in the world for a fixed-wing drone. Here's the range of other applications this same broader bamboo materials push has already reached. According to reporting from People's Daily, bamboo tableware and film bags are now in widespread everyday use. Bamboo composite pipes have been laid into real construction trenches, specifically engineered to handle large diameter pressure applications in urban utility tunnels, and bamboo fiber composites are already being used inside. Automotive interiors, with one chairman in the industry specifically noting that independently developed bamboo winding composite technology can now be processed into components as demanding as high-speed train carriages. Think about what that breadth of real-world applications actually reveals about how seriously this material category is being taken at a national level. This isn't a single university lab chasing one interesting plastic alternative in isolation. It's part of a coordinated multi-industry push treating bamboo broadly as a genuine strategic substitute for both plastic and steel simultaneously, with BM Plastic representing this specific research team's contribution to a much larger, already actively deployed national materials strategy. Here's the honest concession worth sitting with directly, because credibility matters far more than repeating an impressive laboratory result without its proper context. Independent science reporting covering this exact breakthrough has been explicit that, despite BM Plastic's genuinely impressive mechanical properties and biodegradability performance, the path to widespread real-world adoption still requires overcoming real, unresolved challenges specifically related to production scalability and market acceptance, meaning the highly controlled process used to create and test this material inside a research laboratory still has to be proven capable of scaling into genuine, affordable mass manufacturing before it could realistically start replacing plastic on store shelves anywhere. Here's a second honest limitation worth including directly. The researchers' own published findings note that the real-world decomposition rate of a finished industrial product built from this material may vary depending on temperature, humidity, soil composition, and the specific thickness of the material involved, meaning the 50-day biodegradation figure reflects a specific tested condition rather than a universal guarantee that would apply identically in every climate and every use case a real consumer product might actually encounter. Think about why both of those caveats matter so directly to how quickly this technology could realistically reach ordinary consumers, proving a genuinely strong, genuinely biodegradable material is scientifically achievable. Inside a university, laboratory is an enormous and genuinely difficult milestone on its own, but manufacturing that exact same material reliably, consistently, and affordably at the volume needed to replace even a meaningful fraction of global plastic production is a separate, considerably larger engineering and economic challenge that remains ahead of this research team, not already behind them. Here's why neither of those honest limitations actually diminishes the significance of what's already been proven here, though. Solving the fundamental scientific trade-off that had stalled this entire research field for years, strength without sacrificing biodegradability, represents the hardest part of this multi-phase journey being genuinely completed, the exact foundation any future scaling effort would need to build on top of. So here's the full picture, start to finish. Conventional plastic's remarkable strength has always been inseparable from its environmental cost, while biodegradable alternatives have consistently traded that same strength away in exchange for breaking down safely in soil, a trade-off that had defined this entire materials research field for years. Researchers at Northeast Forestry University and Shenyang University of Chemical Technology solved that exact trade-off by completely dissolving bamboo cellulose down to the molecular level, using a non-toxic solvent, then deliberately reconstructing a denser, more optimized hydrogen bond network than bamboo's own natural structure, producing BM plastic, a material that matches or beats conventional plastics like PLA and ABS on tensile strength and thermal stability, fully biodegrades in soil within roughly 50 days, retains 90% of its strength through closed-loop recycling, and can be manufactured using the exact same injection molding equipment already used to produce ordinary plastic today. That breakthrough sits inside a much larger, already actively deployed national bamboo material strategy, one that's already put bamboo composites inside a flying drone's fuselage, real underground utility pipes, automotive interiors, and even high-speed rail components. What you're actually looking at in this story is the same shift that happened decades ago when synthetic fibers first began challenging natural materials like cotton and wool, not because the old material had stopped working, but because sustained materials science research finally closed the specific performance gap that had kept the alternative out of serious consideration for so long. This bamboo-based plastic hasn't replaced conventional plastic on store shelves yet, but for the first time, the core scientific trade-off that made that replacement seem impossible has genuinely been solved. If breakdowns like this, the real research and the real limitations behind China's biggest material science breakthroughs, are useful to you, hit like and subscribe, because there's more of this coming, including a closer look at what happens the first time BM plastic actually gets scaled into a real manufactured consumer product, rather than staying inside a research paper. So here's the honest question. For the comments, does a plastic this strong that still disappears into the soil within 50 days make you think we're finally close to solving plastic pollution? Or does the real gap between a lab breakthrough and genuine mass manufacturing make you want to see this on an actual store shelf before you believe it? I read every single one.